This one will be fun to edit. I'm looking forward to the pancake timeline. Hello everyone and welcome to OpenCV Weekly Webinar, episode 60, if you can believe that. I am Phil Nelson, your co-host with the co-most. Dr. Satya Malik is on assignment. With me this week is Anna Petrovicheva. Anna, would you like to say hi?
Hi everybody, and thank you so much for joining today.
Great. Always a pleasure to see you, Anna. And our guests this week are Team UCA Robotics, the second place winners in OpenCV Spatial AI contest. We're super excited to have them here. Their project was about human-robot collaboration and making that safer through artificial intelligence and machine learning. Before we introduce them, I'd like to remind you of a few things we do here every single week on OpenCV Weekly Webinar. First of which is a trivia giveaway to one of you lucky winners in the Zoom audience. If you're not in Zoom, you can get into Zoom by going to opencv.live. Later in the webinar, I will ask one question to you in the audience, and the person that answers it correctly will win $200 of Microsoft Azure training credits from our sponsors at Microsoft Azure on blazing fast Intel hardware. We're also, we're also taking Q&A from you in the audience. So at any time you have a question, use that little Q&A button in the bottom of your Zoom window to ask a question, and we will do our best to flow it into conversation or save time at the end to ask those that we don't get to during the presentation. Now, Team UCA Robotics with us, we've got Francisco Badesa. Francisco, welcome.
Hello, everybody. I'm Francisco Javier Badesa. I'm a postdoctoral researcher in the University of Cádiz in Spain.
Right on. Thanks, Francisco. We've also got Miguel Lopez Fuster. Miguel.
Hi, everyone. I am Miguel Angel Lopez. I am a PhD student. I have been working on IT since 20 years ago, but I am now doing my PhD on robotics and artificial intelligence.
Awesome. Welcome. And last but not least, we've got Arturo Morgado, who will be starting off the presentation. Arturo, a little bit about yourself, and then go ahead and start sharing that screen. It's your show.
Thank you, Philip. Hi, everybody. I'm Arturo Morgado. I'm professor of University of Cádiz. I'm PhD in engineering, and now my colleague Francisco and me are leading the master thesis, of the Miguel, and this is very interesting because the topic is related to the vision artificial intelligence in industrial robots, and therefore we are thank you for creating to OpenCV Spatial AI contest event. It's very special for us.
Thanks. It was very special for us as well. And again, thanks to our very generous sponsors at Microsoft Azure and Intel.
Thank you. Okay.
Let's rock and or roll.
Okay. About the production line with a lot of robots working without worker. Okay. Well, the typical robots, the classical robot, the brand is KUKA, FANU, Motoman, ABB, etc. And all of them are directly related to the color. Normally, KUKA has the orange color, FANU yellow, Motoman blue, etc. But this is the classical robots. Okay, this is the robotic arm of freedom, degree of freedom. The problem, what's this? The classical robot need to collaborate with the human, and there is and it's possible and it's necessary to collaborate near them. For us, to increase the human-robot collaboration, it's necessary that the robots or around the robot have a lot of system to safety the security of the human. For that, imagine the typical optical barrel or the other thing is normal in the industry. When you try to or define the workspace between the human or the worker to the robot, it's necessary to have a protocol to work between with them. In this slide, we can see a lot of way to collaborate with the robot. Okay, when the robot have not safety system, it's necessary to the robot has far for the human. When you need to collaborate very near, very close for them, it's necessary that the robot has a protection, or the robot detect the in this case the force or the collision for the human or for the other thing. Okay. For that,
this is necessary for for the audience here who maybe isn't a professional in this field, or maybe has never worked with industrial machines, for example. I saw a very funny sticker the other day which illustrates this point well, and it said, "This machine cannot tell the difference between metal and flesh, nor does it care."
Yes.
Yeah, that's exactly why we need things like this.
Yes, for that it's necessary to have this protection. Now there is a lot of collaborative robot has detect the collision, but it's not enough for the work between human and the robot. Okay. And normally, all of them think in use defense or gate or whatever thing to separate the human for the robot. For that, from 2011, there is standards of the collaborative robot, and there is and they define the way to collaborate human and robot. There is 4 types. The safe for stop monitoring. It means that when the human works near the robot stop. Okay. For that, the robot inside or around the robot needs element to safety the security of the worker. The type of is high guiding. High guiding is move the robot. It's only a small pieces the robots. The type 3 is when a worker is very close of the robot. The robot is not stop. Is move more slowly, but it depends the distance. This is a particular way to increase the work of the robot, and this is our project is related to this idea. Okay, and the fourth of the type 4 is the collaborative robot. Has this characteristic is they can move the arm with the hand of the human, and and they can program, or they can move the robot and whatever part. For that, this is in general, this is the introduce, and my colleague Javier are going to talk about the Spatial AI for Safe Human-Robot Collaboration project.
This is a really interesting slide here. If you could put that slide back up for me? I'd like to talk about it for a second, if you don't mind. Yeah, type 3 speed and separation monitoring.
Okay.
So what's interesting, what might not be obvious here is that some workspaces, people routinely have to move nearby these large industrial robots, and you don't want them to stop entirely, because that greatly reduces the amount of time they will actually be active and working. But
yes,
you can't have them be going full speed, because somebody very may well get hurt. So yes, it's a balance between what is a safe speed and what tasks can it do, so people can safely pass based on how nearby people will pass and how often. And so this is it's a very serious problem, especially in these larger scale manufacturing, where this robot arm may be 15 feet tall. Like it may be several meters tall. Like it could be huge, and have tons of force behind it, literal tons of force. And so they're not going to stop it entirely, because they have goals to meet for production and things like this, but they need it to slow down, and figuring out exactly how much to slow it down and what tasks it can perform safely while it's slowed down is a really important thing for human safety.
Yes. Now the type 1 is very, very easy to get, because it's only a optical barrel, and when you pass the optical barrel or whatever contact, the robot stop.
It's a hard stop.
Yes, the type 3 is very complicated, because it depends on the distance of the human. The barrel is only gets the two rounds or two off the robot. Other thing is use the leader. Leader is element to get the distance between one element. So now the leader is possible to get the type 3 level. In our solution, we use the camera to get the type 3. Okay.
Yeah, thanks to low power edge devices like OpenCV AI Kit, it makes these type 3 type of situations much more achievable and much more affordable.
Okay.
All right. Yeah. Continue.
We continue, and my colleague Francisco explain about the project.
Yeah, I'm going to continue the presentation. Thanks. I'm going to continue the presentation. So Arturo has introduced the problematic about working together, the human with the robot. So in the last years, it's very common the need to share the same workspace between the robot in order to do different tasks, such as assembly tasks. So the main goal of our work for the contest is to implement a safety assurance on general purpose robotics in order to provide collaborative features at manufacturing workspaces. Okay, for that purpose, we use the OptiLight cameras, and the idea was for a robot to be certificate such as collaborative one, it needs to have one of these 4 types of safety features. And we try with computer vision to address 3 of these 4 types of security.
How do these,
for-
can
Yep.
I interrupt there to ask, so I think you mentioned a certification, like how do those certifications work?
But this is because the robotic system had to pass different like exams for the certification, and you have to assure that your robot has one of these 4 types of security, of safety assurance.
Is it like a self-cert, or does a person come from the, ISO or whatever to verify things?
No, I think it has to be an official, I don't know,
Okay, cool.
organization, no? To certify this kind of robots.
We've got one quick question from the crowd here. Abkul would like to know, is the camera auto or fixed focus?
It's autofocus, the one we use.
Okay, thanks. All right, continue.
Okay, so for our project, we thought about 4 main blocks. These 4 blocks are computer vision. The computer vision we used for implementing the safety assurance, the robot device, because we need to interact with a robot device, and one of the most important blocks here is also the information management between every device, because we have 1 or more cameras. Each camera is sharing different information, and we have a robot that has to use this information to change its behavior. So this is an important block. And also we have the task definition. So we try to define a simple assembly task because we didn't want to think about a complex task, but a simple one, because the important thing here is the safety in the interaction, but not the complex of the task. So I'm going to talk about the computer vision block. So for this, we implement a perception stack. We try to implement 3 different things. The first thing is person detection and recognition. The second one is human pose estimation, and the last one is not for the security, but is for the collaborative task, is the object pose estimation and task supervision.
I like that you're using the term perception there, because I think that really, I see that being used more and more lately. Over years, it was sort of a small, you had very few people talking about perception with spatial computing and computer vision. And I think that's really what's happening here, because not only do you get the visual, but you have, depth, you have understanding of what the camera's looking at. And so perception is the right term here.
Okay, so for this first part of the perception stack, we have the person detection and recognition. The main goal here is to modify the behavior of the robot depending on the distance of a user, of a human. So this part of the perception stack is related to the standard, to the type 1 and type 3 safety features of the standard. We have implemented with two deep learning models. We use 2 pre-trained models, which are face detection and face recognition for OpenVINO submodel. Here in this slide, we can see about a block diagram about what we did with these 2 models. So we have 2 parts, the parts for the 2D image that the oak delight is providing us, and the other part is for the 3D information. So what we did here was to the RGB image, process this image to with a neural network for face detection in order to have a bounding box about where is a face. The result of this neural network is the input of two parts. One part for the spatial location calculator in order to have the 3D information about where the person is. And the other input for this output of the neural network is a cropping manipulation of the image, and another neural network, which is the face recognition from OpenVINO. And the output of this face recognition neural network is a feature vector that we use with the Gaussian similarity in order to know if we can recognize this person as authorized or not authorized. So here in this slide, we can see more or less the pipeline we implemented inside the camera. So we used different nodes from the depth-eye API. And we use a script node in order to manage different information that is sharing between the neural networks and the spatial location calculator node. So here we can see two images. We can see in the upper one a person whose face is detected, and we can see the bounding box. And in the lower one, the lower image, we can see the point cloud that is provided by the information of the two monocameras that the OT light has. And we can see that we have the 3D information of that person.
Quick question from me. Did you at any point try other models and found them to be not performant enough or not accurate enough, or were you kind of lucky and the off-the-shelf OpenVINO model, Zoo models just worked great out of the box for you?
For our case, we didn't have enough time in order to try another different models or to try a personalized one, and we used directly those from OpenVINO's model that works fine for us.
Yeah, great. Yeah, I mean, the OpenVINO models, it was great, especially for these sort of edge computing tasks. Shout out to our friends at OpenVINO. How you doing, Ray, Ragesh, Kevin, Paula? Go ahead, Francisco.
Okay. So here in this slide, it's only a little block diagram again, but Miguel is going to talk about this in the following slides. But it's about this slide. It's about how are we using this spatial information. So the face detection, we use the face detection in order to know the distance from the user to the robot. The recognition, we use the recognition in order to know if a person is authorized or not to be working near the robot. And we also use this information in order to change the behavior of the robot. If the person is not authorized and is near the robot is going to stop. And if the person is authorized but is near the robot, the speed of the robot is changing depending on the distance. Okay, here we can see a video. And what we are going to see here is a person that is not authorized. So now he's near the robot, and the robot stopped its movements. So and now when he leaves, the robot continue his movements, and when a person is authorized and is near the robot will change its behavior, but changing the speed depending on the distance of the robot. If the person is authorized but is too near from the robot will stop.
That's very cool. So what's to summarize here again, it's doing type 1 and type 2 here,
3.
I think, or
type
1 and type 3.
Yeah.
So type 1 if somebody sits down and it doesn't know them, or it knows them but knows that they're not authorized, it will stop entirely. But if an authorized operator or collaborator sets down, then it switches to type 3 mode and slows down and changes what it's doing, which is great.
Right. So the second part of the perception stack is the human pose estimation. In this case, what we are doing here is to hand guide the robot using computer vision. This is related to the type 2 security feature, which is hand guiding. Normally in certified collaborative robots, this hand guiding is performed with an force sensor, which is addressed at the end effector of the robot. But here we wanted to use the 3D information we have with the cameras to mimic the same behavior. Here in this slide, we can see again a block diagram. Here we are using other two pre-trained models from MediaPipe in this case, which are the hand palm detector and the hand landmark detection. Here we can see it's similar to the other perception stack part. We have the 2D image processing in the right, and the 3D processing in the left of this slide. So we can see that we use the RGB image to detect where the hand is. We crop the image, and we can detect the landmark of each part of the hand. And also with the hand detection bounding box, we can estimate the 3D position of the hand. Okay, in the same way, here we can see how we did the implementation of the pipeline inside the camera. We use again different nodes, and again, one of the most important here, one of the important nodes here is the script one. The script node not only use information from the neural networks to use in the spatial location calculator, but we also use the information with the external PC in order to extract the information of the hand landmark model. For this, our implementation is based on that one that is put here in the slide. And again, with this part of the perception stack, we wanted to do two things. One is the hand position estimation. The hand position estimation is for knowing how are we going to move the robot, and this movement will be proportional to the movement we are doing in a 3D position of our hand. And also we have the gesture recognition, and with this gesture recognition we can do different things. The first thing we can do here is, for example, if we close or open our hand, we can close or open the tool that we have in the end effector of the robot. So here we can see in this video the result of this part of the perception stack. We can see that we have the detection of both hands, and if you can see also, we can differentiate between the right and the left hands. Here you can see in the 3D part of the video, in the right part of the video, we can see the position of both hands in the 3D manner, and we can see that the right hand is decoded with a yellow sphere, and the left one is with a blue sphere. And the last part of the perception stack is the object pose estimation and task supervision. This is not related to the security or the safety assurance levels of a collaborative robot, but we thought that is another important feature or other important task we can do with these cameras and with the information, the 2D and 3D information we have with these cameras. And the main goal is to help the operator to perform the assembly task in a correct way. So here in the picture, we can see that we are recognizing three kinds of Lego parts with the blue, the green, and the red one. And we can see also big spheres like we have a green when this part is in the correct position, and red when the parts are in an incorrect position. In order to perform this part of the perception stack, we use two deep learning models. The hand palm detector, we use again the hand palm detector from MediaPipe in order to know where the hand of the human is. And the custom object detection neural network with YOLO V4 light. And here we can see the pipeline we implemented inside the OT light camera. In the right part of the slide, we can see in the upper image the result of the YOLO V4 light model. We have three different Lego parts, and we have the goal these parts as blue, green, and red ones. And in the lower picture, we can see the 3D point cloud and the position of these three parts in a 3D space.
Another quick question with regards to YOLO here. Did you think of did you try any other frameworks for object detection aside from YOLO, or did you just kind of get lucky and YOLO V4 worked really well for your purposes?
No, we used also SSD, but with YOLO we have better performance with lower number of pictures.
All right.
So what we did was to define three kind of parts, which are those we can see in the left image. And we use RoboFlow for image labeling and data augmentation. And we thought to use different platforms to train the neural network, but finally we use our own PC with the darknet implementation of the YOLO V4 Lite. So finally we finished with three different Jupyter networks, one for the data preparation in order to have the correct files to train our neural network, another one for the training, and the last one for the blob conversion. And we use a blob converter for this issue.
So people are going to ask, so I'm going to get out ahead of it here, about how many images did you need to train this model?
Well, we didn't need too much images because finally we were in a very controlled scenario. So we took about 50 images, I think, and we used the data augmentation from RoboFlow in order to have an augmentation of that pictures. So we didn't use many pictures, but because we were in a very controlled scenario.
And so you used a lot of the augmentation tools in order to expand the data set there. That makes sense. About how long did it take to train the model? You said you did it just on a machine there locally?
Yeah. But I don't remember very well, but I think about, I don't remember, maybe 2 hours.
Really, that quick?
Yeah, I
That's
think
surprising.
it was very fast because there was not too much images.
Yeah,
and the result was very good.
Yeah, you're lucky to have. I mean, being in university team, I guess it's more likely that you'll have access to that kind of hardware than some of the other teams that were more hobbyist types, especially these days where we're still in such a shortage for GPUs and stuff like that. But yeah, go ahead.
Okay, so and here in this slide we can see again a little block diagram about how we use the information we collect with the cameras. We use the object detection in order to know where which parts are in the scene, and in order to know the 3D position of these parts. And with this information about which parts and the 3D location of those parts, we implement a little bit, code in order to know if the order is correct or not. And we also use the gesture recognition. I'm going to put another video, the last one I'm going to put. And here we can see that we can move the parts, and we can see in real time if the parts are in the correct order or not. And if the hand the gesture recognition is used in order to learn a new order for these parts. So the idea is that we easily can tell the system an L with our hand, and this L is to learn that the position of the parts in that moment is the correct one. So it's kind of live programming of our task.
Did you teach the robot to play 3-card Monte or the shell game? You could sell it to the carnival.
This is only a simple task. And this is the last slide I have here in my presentation. And now Miguel is going to continue with the rest of the slides.
Okie doke.
Okay.
Well, actually, before we do that, let's we're at about 9:45 here, about 45 past the hour. If you could go ahead and unshare your screen, Miguel, real quick. So I'm going to do our giveaway before we continue with the presentation, if you don't mind.
Stop.
Thank you. Awesome. The way this works is I'm going to ask a trivia question to you in the Zoom audience. The first person that answers that trivia question correctly in the chat in Zoom will win $200 worth of Microsoft Azure training. Now, our guests here on UCA Robotics used a local system to train their model, but they could have just used Microsoft Azure, which most teams in the contest did, and it saved them a ton of time and also gave them access to resources they wouldn't normally have. So thanks again to Microsoft Azure for supporting the contest in that way and giving us access to those super fast Intel hardware. If you have won a trivia question here on OpenCV Weekly Webinar in the last 2 months, please do not answer and give someone else a chance to win. So our team here is from a university. Which university is that? Answers away in the chat. Full name of the university.
Calix is near.
I think I stumped him finally. It took me 60 episodes. There we go. Looks like Jose got it. We're gonna count that one, Jose. Congratulations, Jose. Universidad de Cádiz. send one email to phil@opencv.org, and I will make sure that you get your free credits thanks to our generous sponsors. Miguel, go ahead.
Okay, I will share my screen again. Okay, so as Arturo told, we have a goal, and as Javier has told, we have a camera that gives us a lot of information, but we need a robot to to get the goal. So we use the Mindstorm Lego Inventor 51515 set.
This is a really popular set during the contest. I think probably half the teams use this one. Yeah.
Yeah, we selected this because it has 4 motors. It has a color sensor that it was useful for us. It has a lot of gears to make some reductions. It has a control brick that can be programmed. So the brick has Bluetooth communications, and we read that it was MicroPython programmable. It has a well-documented API. So at the beginning, we made some testing with block codes, but we need some low-level programming to get into the brick. The kind of motors that brings the set has a lot of info. It's not a simple motor. You can control the speed, the angular position. So if you have the motor in the 0 degrees, for instance, you can say add 25 degrees. Or you can say from beginning, you can say put it 45 or 50 or something like that. You had the feedback about the position of the robot. That not all the motors give you that information.
Being able to do absolute and relative changes is really important for stuff like this. Otherwise, there's you got to do other sorts of state knowledge and maths and kind of trying to guess. But if you can just say, go 10 degrees from where you are now, that's so much easier.
Or you need more hardware because you need something to count the laps or something.
Right. Yeah.
So we have 4 motors. So we try to get a 4 degrees of freedom robot. So we made some designs. We use the program called LDraw. And we can make it inside the LDraw. There are a lot of Lego sets. So
I'm surprised I haven't seen this tool yet. We've had probably 5 teams from the contest. I have not heard of LDraw yet. This is very cool.
It was a surprise for us too. So we use that because we can design the model. If not, after that, we are going to use the model to integrate it in ROS. And if we don't have this model, it was so difficult to make something very similar. So we saw that we can export this model to another format and then to DAE, so we can use it later. And then once we designed the robot and we see that we can make some movements with the robot, we decided to build it. And we make some simple tests with block code to see how it moves and so on. So we have the cameras, we have the robot, and now we need to decide what to do. So we decided to make some simpler tasks where we can arrange some pieces and decide which will be the correct sort order, and then try to help to the user to know if the order was correct or not. And then we try to make that if the order has to be changed, that it was easy to make the new order, to set up the new order, not to try to change some file or something. And this was the goal. And because we have a lot of information from the cameras, and the robot also was asking for information and giving information, we need something that can link everything together. So we decided to use ROS. ROS is it's called Robot Operating System, and it's a framework that lets you build robotic applications. It brings you a coordinate frame where you can put everything together, and it brings you a lot of drivers for a lot of cameras. For instance, the OACD that we use has his own driver, and you have a lot of other libraries that let you make the things very quick, because you can share those libraries in different projects. And also the Depth AI brings us a special detection message that is the message used in this project. The message is used because you develop some nodes, and all those nodes share information via the passing of those messages. Unfortunately, the Lego brick lack of support of ROS, or at least we don't have found anything about the Lego brick and ROS. So we have to develop a special driver for this brick.
ROS will be well known to many of the habitual viewers of OpenCV Weekly Webinar. We've had Kat Scott, the developer advocate for Open Robotics, on the show a few times. And in fact, they just released ROS 2 Humble Hawksbill recently. So congratulations, team, on shipping that. We're gonna have to try to get ROS and Lego to have some official collab, right? next contest, it'll be important.
We have a GitHub with these with the things that I'm going to share in the next slide. I can tell you. We designed we build the robot, so we try to pass this robot to ROS. So we have to make the WordDF file where we have to define the links of the robot and the joints. So we have to explode the robot in different links and make it work on ROS. So after we have that, you can see this is a screen from RB's tool from ROS. And once we have this working, we have to make it move. So we try to make something general that not only will work with the Lego robot. So we wanted, as you can see, I don't know if you can see here, but we have another robots, and we wanted to use it later with these robots. So we decided to use robot control. Robot control is a generic robot controller made on ROS. So many of the things are already defined, and you only have to define the orange box here. So we need to develop this orange box for the Lego brick controller. We have developed that part, and we have shared on GitHub.
Awesome, that's very cool. Always happy when people open source things.
Okay, thank you. For this part, we have developed the hardware interface part of the Lego brick in MicroPython. The robot, the host, it's a laptop and communicates with the brick via Bluetooth, and it works very well. And we only have had some problems. That is that the robot needs to be connected to another laptop via USB cable, because if we quit this cable, the Bluetooth, we don't know why still, but sometimes cut the connection. But if you connect the brick, the Bluetooth works very well. And then we connect the Lego brick to the laptop via Bluetooth, and then the Lego brick send the feedback information from the motors to the host, and the host send the command when that is all the movements that the motors have to do to reach the desired position. and you only have to say the robot where. So you only have to say to the laptop where do you want the robot to be, and then the hardware interface make the ROS control make the magic. Okay, so we have the cameras, the robot, and we need to develop some nodes. In ROS, you develop nodes that takes information from another nodes and give information back. So we have two nodes, Lego controller and Lego inventor. Lego inventor is the ROS control interface that we have explained before, and the Lego controller is the abstraction layer that says take one piece, go back, give one lap, or something like that. And we take the info that came from the camera one, that is the camera that is facing the user, and we process the information from the camera and then give back the info on the form of messages that can be consumed by another node. So in the camera that is facing the user, you can see the face, it detects the face, it gives you the name of the person, it gives you the X, Y, and Z of the head, so you know where it is in the space, and it's everything encapsulated in a message. The nodes, when see someone that is when sees the name, checks against a database, and it says if it is authorized or not, and it slows or stops, as Javier told before. I will try to be quick on that part. It also runs the model of the hand gesture, and it says which hand is, and the bounding box, and so on. So you have information, and you can take decisions. Okay. And when you know the hand gesture, you can now, what are you asking for? So you can make the sign for the learn order. You can ask for the first piece, the second piece, or the third piece. And when you perform the programming, you can move the hand to know when you want the robot to move, and you can perform the gripping, opening and closing the hand. And for the task, you know which piece has and where it is, so you can order in a space in a different axis, and you can know the order. So you can paint the spheres that we see before and so on. And when you perform the L, you can save this order, and you can save it as the new order. But I think I have explained this slide. So once you have the info from the camera, one camera is facing the user and one camera is facing the scene, you have everything in the frame of the camera. So if each camera is facing each other, for instance, the setup, it will be on the negative. So we need a coordinate frame for everything. So in ROS, you can use a coordinate frame where you can put everything together. You can make an extrinsic calibration from the cameras to the robot, and then everything is in the same frame. We have used the robot as the 0. So you can see here is the slide of the robot. And you can see the reference from one of the links that conform the robot. The cameras are not here, but you can imagine that the cameras are each one on the side, but all of the coordinates are referenced to this reference frame. So, well, I think that in the other slides, there was a small graph that it was showing the nodes about each camera and the nodes about the Lego inventor and the Lego controller. And this is the full node that connects everything together. When any camera sends the hand or something, it's publishing the info about the hand, and then gets into the other node. It processes, sends it to the other node, and we can see everything in action. I will try to explain quickly the things that are happening here. So in this case, I am not authorized. So the robot stops. And now Javier is authorized. So the robot keeps working. And if he gets closer, the robot stops or slows. This is the programming part where you can move the hand and can open and close the hand to grip the piece. As you can see, it's quickest than Rian.
Yeah, the latency is nice.
And this is the supervision. That this is the task where you can see if the arrangement is correct or not. This video from the right, it's directly from the Ubuntu, so it's saved from the Ubuntu. So these jumps are not from the camera, are from the laptop. And this is the full task. Arturo is not authorized, so it can change the pieces, but the robot doesn't move. Javier is authorized, so the robot says okay and moves. And when Javier wants a piece in the new order, it gives him.
I want one of these like at the sushi bar, you know, I can just reach up and grab and put it on my plate for me.
Well, okay, this is we can cut here because I think that this is almost the same that we have told. So when in the last when you give the prices and so on, you were talking about that it will be good to see that working on a big robot. So I think the price event, it was on Monday, and on Wednesday we have some tests. We did some tests.
Wow, you said you had a surprise. You weren't kidding.
Yeah, that was a surprise. For us, it was a surprise too, because we designed that to be working on a big robot. We have experience on the war, but we didn't know if that it was going to work so quick. But it was working 2 days later.
That's incredible! Wow. Yeah, from Lego to industrial robot in just 2 days. That's heck of a quick journey.
You can see the cameras there.
Mm-hmm.
Oh, you can see the screen back in the TV. So it has been a good experience
That is so cool.
to work on this contest.
Just wow.
Yeah. Extremely cool. So what's the name of this particular robot arm?
This is an UR5E. I think
Very cool.
I can see my screen, but when I leave the screen sharing, I can show you.
Cool. Yeah, most people probably do not know this, but for a long time at my old job at Occipital, one of our internal running jokes was robot arms. We were always, we only raised money till we could buy robot arms. That was the that was the joke. And so this is very cool to see. Gosh, yeah, I'm really amazed that you were able to take this contest project built on Legos, and then in 2 days apply it to, an industrial scale robot. It's mind blowing to me. I'm really impressed.
This is actually the reason why we wanted to do this competition, right? We wanted to make it real for some robots, right?
Exactly.
To do stuff using Oak with computer vision, right? So yeah, truly amazing.
Yeah,
I have to say that
impressive.
we did not see this video at the time when we were ranking the competition, right? So the competition video was mostly focused around the Lego. So for me, I'm truly amazed right now.
Yeah, that's what they were saying, is they implemented this right after we had announced the winners, I think, and but I mean they still got second place, so not too bad.
Well, we were lucky because the deadline, it was on Friday, but you extended to Monday, so we can finish.
Hey,
so
if there's one thing I
didn't have
know,
time.
yeah, if there's one thing I know, it's that engineers love to wait to the last minute, because I am an engineer and I like to wait to the last minute too. But yeah, you nailed it. It's a heck of a project. So we've got a couple questions here. An interesting note here from Howard in the chat. Howard asks, are you aware of the NIST draft on risk management with regard to safety? Apparently he's a member of the IEEE Artificial Intelligence Standards Committee and is looking to formulate a recommended practice of a tiered approach to this problem. Do you think on the team, do you feel that this would help folks in your area that you're working on now?
I don't know if Javier
you haven't heard so yeah, according to Howard, this NIST draft is extant. He posted a link here. I'm going to go ahead and post it in the chat. Very interesting. Another question here from Ken Gish, who would like to know, what are you planning to do next, Team UCA Robotics? Are you planning to do any more work on this project? Are there some parts of it that you want to maybe polish up, or are there some parts that still need to be released as open source? Are you going on to new projects? What's next for y'all? We'll start with Francisco.
Yeah, I think the next step is to make real the Lego implementation. That video we show is like Miguel said, today is a fast implementation of the same system with Lego, but we want to make a more realistic task with this kind of safety with computer vision. And this is not our real field of research, because we are working with industrial robots, but not in these kind of fields of collaborative robots. But I think we are starting a new research line.
That's great. Yeah, you've got a great start here. Miguel, what about you?
We are working with these cameras because we have tried to make our own models, and we are using on another project because I don't know if you can see, but there is a welding.
Yeah, big yellow robot arms back there.
A welding robot, and we use expensive cameras to try to see the thing and try to detect the points that we want to weld. And we are using these cameras to make more or less the same things. Still has a little small precision, but we are near the result of the expensive camera. So we are using those kind of cameras, and I think that we will make something on this line too, on collaborative robotics and so on.
Yeah, right on.
And I hope we can participate in another contest. I don't know if there will be another soon.
Yeah, I hope there will be another one soon too. Arturo, thoughts? What's next for you?
Well, I suppose that is hear me? Okay.
Yeah, you sound good.
Okay. My next step, or my step is to make a lot of elements in the hands of the robots. Imagine tweaks or elements that because in our laboratory there are a lot of machine, CNC, CD printer, a lot of machine to make or manufacture these systems.
Cool. So you're saying some more maybe custom sort of things for this collaborative robot system. It's awesome.
Yes.
Yeah, Anna, some thoughts, questions. You've been quiet over there.
I'm still in a kind of bit of shock after seeing these, like, real big industrial robot like costing. I can imagine how much doing these kind of, it seems like as if it was an intelligent creature, kind of like an animal, right? That kind of serves the kind of commands of the user. So this is the kind of, I would very much vote for the team to continue the research and the great work that you do. And I mean, just thank you for participation in the competition. It's really heartwarming to say, to know that it really kind of connects the state of the team where you don't research for the robot, for kind of the big robot. It's an intermediate step between the research and working with a big robot. So kudos on that.
Yeah, these intersection of research and implementation and cutting edge tech is why we do these contests to begin with, is to try to push these things forward and in the best way we can, which from OpenCV's perspective is to help as many people as possible put their minds to these new tasks. And so yeah, it's so gratifying to see such incredible results from all of these teams, especially our prize winners. Congratulations again to Team UCA Robotics for winning second place. Let's see what else we've got. Next week, our guest will be Deep Cut Lab. They are doing some incredible work with pose estimation for animals like lab rats and stuff like that. It's really interesting stuff. I'm always excited when we can have more sort of like hard science stuff here, such as this project and Deep Cut Lab. But really looking forward to that. That'll be next week on Thursday at 9 a.m., same bat time, same bat channel. We are also still working on the OpenCV virtual set, which is probably going to debut soon. It may be next week, it may be a little bit later than that. We'll see how it goes, but you're gonna love it. We are still not announcing a new contest yet, but if you are excited about the next one, if there's going to be a next one, please send us an email, newsletter@opencv.org. Subscribe to the newsletter. That's the best way to find out when the next stuff is happening. We also do giveaways for OAK-D Lite, OpenCV courses, things like that. So opencv.org/subscribe is the best way to get that stuff. Team UCA Robotics, what is the best way if people want to follow what you're working on next, or just find you on the internet? What's the best way to do that? Francisco.
So the best way, I'm not sure, maybe with in our webpage and maybe in Twitter also. But we are not very how to say.
You're saying you're not terminally online like I am?
Yeah, we didn't publish many things, but I think in our webpage is the best way to know from us.
What's
and we are trying. We are
that?
trying. I don't know, Arturo. Which is our webpage? I think we put it in the presentation.
All right. Yeah. Well, I'll drop it in the show notes.
In the first slide, there is the address and the link to the to know about our works in the university.
Awesome. Yeah, I'll drop that in the show notes for folks when we upload this to YouTube. This is going to be a fun one to edit. I'm already looking forward to it. Thank you so much to our audience for joining us. As always, we only do these shows because you watch them. We really appreciate it. Join us next week, Thursday, 9 a.m., same bat time, same bat channel. One final thanks to our sponsors at Microsoft Azure and Intel. We hope to do a lot more stuff with them in the future. Everybody, take care of yourselves out there and take care of somebody else. Thanks so much for watching this episode of the webinar. Please hit that like button, subscribe, and don't forget to tap the little bell icon to be notified when new episodes drop. This week's episode was brought to you by Intel and Microsoft Azure as part of OpenCV Spatial AI Contest. Follow along with the OakDLight Contest hashtag. If you'd like to be in the audience next week, subscribe to the OpenCV newsletter.